Okay, we have a fascinating stack of research to get through today. We're looking at, well, a pretty fundamental shift in how science gets done.
It's a huge shift. I mean, you could argue it's as big as the invention of the microscope.
But there's a catch, right? That's what we're digging into. This rise of AI and scientific discovery
Yeah.
and this tension between just getting an answer and actually understanding it, the what versus the why.
Exactly. And a great place to start is this story from back in 2020. Researchers were hunting for new antibiotics, and they used an AI to just churn through millions of compounds.
And have found one, right? A candidate called Halison.
It did, and
Yeah.
Halicin was incredibly effective. It was killing bacteria that had become resistant to pretty much everything else.
Okay, but here's the kicker, the detail from the reports that really sets up our whole deep dive today. They knew that it worked. They could literally see it in the Petri dish.
Mm,
But because the AI found these patterns that, humans just couldn't see, they didn't fully understand how it worked.
yeah. And that's the core dilemma. Science has always been about, understanding the mechanism to predict a result. Here, the result just arrived. The understanding had to play catch up.
So it makes you wonder, is this still science? Or have we just invented a very, very powerful form of engineering?
Well, to answer that, you have to appreciate the scale of the problem. We're talking about them called combinatorial space.
Which is just a wild concept. It's basically the idea that there are more potential drug molecules out there than there are stars in our galaxy.
Right, so you're not looking for a needle in a haystack. You're looking for a needle on a planet made of sand. Humans can't do that. AI makes that search less blind.
But the sources we looked at are clear. AI plays different roles, and each one has its own sort of trap.
Yes. Let's start with the first one. AI as the observer, the pattern spotter.
Like that epic sepsis model they use in a lot of U.S. hospitals.
Exactly. It was built to scan patient data, spot the early signs of sepsis, and alert doctors. On paper, it's a lifesaver. But when independent researchers looked at it,
It didn't work so well in the real world.
not really. In the messy reality of a hospital, with its chaotic data, the model started having, well, illusions. It was flagging patterns that weren't really there.
So false alarms.
A lot of them. It led to alarm fatigue. The doctors just started tuning out the dashboard.
Okay, then there's the second role, the constructor. This is the generative stuff, like AlphaFold predicting protein structures.
The one everyone gets excited about. It creates these beautiful, complex 3D maps of proteins.
But we have to be careful here. A map is not the same thing as a mechanism.
Precisely. Knowing the exact shape of a mountain doesn't tell you why an avalanche happens. AlphaFold hands us the structure, but not always the physics or the biology behind why it behaves the way it does.
A prediction without the theory. And that leads to the third role, the navigator, where AI tells you what experiment to do next. The danger there seems to be optimizing for the wrong thing.
It's like your GPS routing you over a cliff because mathematically that's the shortest path. It can chase a metric that looks great on a screen but misses the clinical reality.
This all builds up to what the readings call the black box dilemma. Let me put this to you. You're a patient. I have two models. Model A is 80% accurate, but we can explain exactly how it works.
Okay.
Model B is 95% accurate, but it is a complete black box. We have no idea how it gets the answer. Which one do you want trading you?
In the clinic, I'm taking the 95% black box.
Really? You'd trust the machine without the explanation.
If the outcome is demonstrably better, yes. But, and this is the most important part, the rules for validation have to change completely.
Wow, so.
The rule has to be the darker the box, the higher the bar for testing.
So if you can't explain the why, you have to be absolutely rigorously sure about the what.
Exactly. You need massive external validation across different hospitals, different populations. We learned that lesson the hard way with IBM Watson for oncology. It looked brilliant in a polished demo, but it failed in actual clinics because it was never properly tested against that chaotic, real-world patient data.
That feels like it creates a whole new problem for science, for peer review. They call it double reproducibility.
It's a huge hurdle. It used to be enough to just reproduce the lab experiment. Now you also have to be able to reproduce the computation.
But what if you can't? That's this idea of locked compute.
Right.
If a discovery is made by a giant proprietary model sitting on a Google server somewhere,
Then you can't verify it. I can't see the code. I can't see the training data. And if you can't verify something, is it still science?
or is it just a product, a press release? You're essentially locking the truth behind a corporate paywall.
That's the risk.
It really feels like we're moving into an era of, I don't know, cheap answers.
That is absolutely the worry. We're mapping the boundaries of what works, but we don't always know why. But if the answer is instant and cheap, are we losing our ability to do the expensive thinking that's required to actually check if the answer is right?
And that's the thought we want to leave you with. If the machine gives us the answer every time, do we eventually forget how to ask the right questions? Thanks for listening to this deep dive.
Keep thinking.